wish you all a warm welcome for this new webinar in the series of IFC webinars we have every month now. I'm Thierry de Dr. Witt, and today it's a real pleasure to welcome Vassilis Angelopoulos from UCLA. My feeling is that most webinars deal with objects that are really nice to look at, like the sun, stars, planets, and so. And as soon as you want to address acceleration processes in the near-Earth space, it becomes really messy because you need all these spectrograms and multi-spacecraft, and people try to move to something else. So for a very challenging topic, you need a very good speaker. And so we're very lucky to have Vassilis with us today. And just a few words, Vassilis is now a professor at UCLA. He did his studies at the University of Thessaloniki in Greece, where he earned his PhD later at UCLA. And he worked on several missions. He's well known for having worked on the Themis mission, and I guess he'll talk about this later, but more recently also on a smaller mission called Elfin. Most of his work is dedicated to the studies of particle dynamics in the Earth magnetosphere. He currently serves on different boards, but I also would like to mention that he received in 2024 NASA's Outstanding Public Leadership Medal, as well as UCLA's inaugural Physical Sciences Centennial Mentorship Award. So he's really well known in our community. And again, I'm very glad that, to have him with us, especially for this kind of topic, which is not easy to address. So if you have questions, please write them down in the chat. We'll be going through the list of questions at the end of the webinar. So if you do have questions, just write them down in the chat and we'll be collecting them. And at the end of the webinar, we have time to hopefully go through all of them. With that, Vassilis, the floor is yours.
Well, thanks very much, Thierry, for the opportunity to talk to you today and for the nice introduction. I'd like to talk about plasma acceleration in near-Earth space as viewed by in situ measurements in the magnetosphere, but also from the ionosphere looking up. And I'd like to start from the fact that we like to expand into our near-Earth space environment as humans. To paraphrase Carl Sagan here, humans are explorers, and we constantly look to expand our horizons driven by curiosity and in all of the world's beauty, that we strive to study and visit places far beyond our home Earth. But hazards are part and parcel of space exploration, from the first Explorer 1 satellite that in 1958, launched in 1958. We know that this dangerous radiation-filled environment is inhospitable to humans and to hardware alike. These radiation belts, you see at the bottom left, are places that are in red and blue hues down here, is where high-energy electrons are stably trapped for long periods, drifting around the Earth, for weeks or months, and sometimes even years. And their fluxes increase and decrease when the space environment is energized, and where those particles are lost because of wave-particle interactions and other processes in the magnetosphere, a complex system. Now, we've since learned that these belts are powered by explosive solar storms, start from the sun and by solar flares. These flares also produce X-rays and gamma rays, as imaged here by the RESI satellite in this compendium of movies of the same solar explosion. And they release billions of tons of matter and huge amounts of energy that come by the Earth and power the Earth's magnetosphere. They create beautiful auroras that you see here on the right, manifestation of this tug of war that's happening out in the near-Earth environment. As a result, the near-Earth space is permeated by dynamic, intense electrical currents that not only damage spacecraft electronics, but they can also harm humans out there. We know that the Earth's magnetosphere is this cocoon-shaped object, as depicted here, that is powered ultimately by the electromagnetic energy that is from the sun that is the motional energy of the sun that transports the magnetic field of the sun. And when that magnetic field has an anti-parallel orientation to the Earth's interior magnetic field, the dipole on the inside, then magnetic reconnection enables a connection of the solar field lines or solar wind field lines to the Earth's own magnetic field lines, imparting motion to them, dragging them to the right, and compressing them on the night side. By compressing, that increases the magnetic energy at the expense of the kinetic energy of the wind. And that energy ultimately is released in the interior of the magnetosphere through another process of magnetic reconnection in the magnetotail here to the right, as depicted on the right movie. That is a trigger, is a spigot that enables the magnetic energy that is previously stored or partly stored in the magnetotail to be released again, now in the form of kinetic energy and plasma heating that occurs much closer to the Earth. So about 10% of the solar wind kinetic energy enters the magnetosphere this way due to magnetic reconnection that enables this process at the day side. The actual conversion happens at these high latitudes where magnetic energy is generated, and the magnetic to thermal energy happens at the equator, all the way from the tail to the near Earth region. The jets that are produced by this tail reconnection then propel the plasma from the reconnection site towards the near Earth environment and power the near Earth space environment, creating these auroras and the radiation belt, powering the radiation belt and magnetic storms. This is what ultimately drives the system. And it creates a very dynamic environment that you see here in an average sense. So this is a space climatology that shows you different regions, the magnetotail lobes where the energy is stored, the field line currents that connect dynamically the drivers of the ionosphere out in space and the ionosphere itself at low altitude, say several hundred kilometers. Plasma convection is depicted here, and the orange region around the Earth depicts the location of the trapped particles that I mentioned earlier, the outer and inner radiation belts, as well as the ring current, a circular current around the Earth that is primarily composed of ions drifting around the Earth and being energized at the times of major magnetic storms. So this is space climatology. Moreover, these phenomena drive at low altitudes the ionosphere. They increase due to heating, ionospheric heating. They increase the scale height of the ionosphere, and that is driven from phenomena up above that contribute to drivers also from down below. So if there were no magnetic field, then only gravity waves and atmospheric coupling to the upper ionosphere would drive ionospheric motion and heating. But thanks to the magnetic field, additional phenomena cause ionospheric heating and large flows in the ionosphere. And then due to the space interactions, high latitude activity creates ionospheric heating, large electric fields that cause ionospheric flows. They cause density variations in the ionosphere, and they cause phenomena like scintillation that affect the radio communications at times of large storms, ionospheric irregularities and phenomena like that. So storms affect the ionosphere in a complex interaction between the ionosphere with drivers from both below and above. And it's a difficult system to study. But it is important, just as important as the radiation belts are for satellites out there and human presence in space, so are ionospheric scintillation effects due to storms. For example, in 1967, at the peak of the Cold War, a solar storm inadvertently set off the US military's nuclear attack early warning system. The North American Aerospace Defense Command, NORAD, system, of which 3 antennas you see shown here in North America, in the Northern Hemisphere. So this system went blank. Suddenly, it couldn't respond. And the thinking was, well, this is some intentional effort to blind the defenses. B-52 bombers like this on the right were equipped with nuclear bombs ready to take off. And the only reason they didn't was concern they would not be able to land back safely due to poor communications. So space scientists quickly exposed this false alarm that was due to a solar flare that caused ionospheric scintillation. But the incident also underscored the importance of space weather monitoring for global security. So back in 1859, it was recognized by Lord Carrington that who was counting sunspots daily and observed the largest space storm event to be recorded at Earth since ground magnetometer recordings were started, that phenomena at the sun, like solar storms, solar flares, have effects at the ionosphere. And that particular solar storm and its effects at Earth was the largest to be recorded ever. But it turns out such phenomena do occur even today of similar intensity. The stereo satellite in 2012 captured a coronal mass ejection that was at a different longitude than Earth. You can see stereo here, and Earth is here. That did not hit the Earth, but it was observed by stereo to be as dynamic, as likely as the 1859 Lord Carrington event. So these events happen even today, and we luckily missed that one. But stereo recorded this approaching CME and the particle ionization in near-Earth space that followed it, and it packed quite a punch. Had it hit the Earth, it would have caused storm effects as large as the 1859 storm, Carrington event, and the cost from such a space storm could be trillions of dollars, according to the National Academy of Sciences study. So this cost is more than an order of magnitude larger than the cost from the Hurricane Katrina. So space weather is of concern and will be of concern for a long time. It affects increased human activity in space, but also has societal effects on observations of agriculture and navigation and so on, including power distribution. So these large space storms can wreak havoc with the distribution of power in transformers, and they can zap those transformers because of imbalance between nearby power networks, and with costs that are very, very significant. So to study such a system, satellites that are positioned at the key locations where this energy comes in, where it is converted, where it is dissipated, these things are important. And that is what the International Solar Terrestrial Program, ISTP, tried to do back in the 1990s. And indeed, it explored the climate of space. That is, from each region, it observed the average behavior of the system at each location, and also loosely explored the connections between the systems. It taught us a lot about the interconnected solar wind magnetosphere ionosphere system at the cost of several $1 billion back then. That was a lot of money. And however, the missions were single spacecraft, so there was spatial imaging. And the spacecraft were launched not exactly at the same time, but at separate times. Overlap was somewhat fortuitous. And some of the satellites, like Equator-S, was lost very quickly in the process. So that bespeaks of the importance of launching constellations of satellites that are simultaneously launched to be concurrent and are distributed over a wide region densely enough to address key objectives. So that is the future. But what ISTP did is prepare the ground for the future. Now, what is the complexity in this? Why is there complexity? The reason is that the circulation of energy from the solar wind to the inner magnetosphere I showed you earlier is not really continuous. It is very abrupt. And so it happens in an impulsive way. So that, and the reason for that is that magnetic reconnection on the night side here is not continuous, it's prohibited for the most part, because the field lines are rarely entirely antiparallel, which facilitates reconnection, but rather they're curved. There is a normal magnetic field to the equatorial plane. And so that tends to prohibit reconnection. And when tail reconnection is prohibited, then the energy coming from the wind is actually stored for a long time in there until something causes that to be released abruptly. That is called loading and unloading, the loading and unloading process of energy that results in phenomena that we call substorms. They're called substorms because they're diminutive, right? It's a small cousin of the larger storms that are much more dynamic and much more intense. So storms can occur maybe once a month during the peak of the solar cycle and the declining phase of the solar cycle. But substorms can occur several times a day. They're weaker, but they have an advantage that they're repetitive and they've been observationally, they've been well characterized. So we know that the phase in which the energy is stored is called the growth phase of the substorm. We know how the auroras move then. The energy release phase, or the substorm onset phase, is when this energy release is triggered by something. People didn't know exactly what that was. I'll discuss this momentarily, causing the substorm expansion phase onset that causes the auroras to expand forward and break up into pieces, brighten, and then the recovery phase, the third phase of the substorm, where the auroras at high latitudes wind down in terms of their intensity and eventually move back equatorward towards the original location at about 65 degrees latitude. Here's a movie of a substorm as it goes on the bottom left. You can see this movie is taken from up above the north, from the image satellite with an FUV camera that is not affected by the daylight. So day and night cannot be distinguished here in FUV. So you can see the auroral oval from up north. You can see a brightening of this aurora at this location, and then a forward expansion of the aurora. You can see the breakup into little pieces, and then an eventual winding down of the activity during the recovery phase. And here's another substorm. Breaks up, moves forward, dies down. this is a sequence repeating every, I don't know, 5 hours, 6 hours, a few times during the day, depending on how intense the magnetic field of the solar wind is, and how often does it turn southward, that is anti-parallel to the interior field, such that energy can be imparted in the magnetosphere. So the magnetotail lobes sort of integrate that energy, store it for a while, and then release it abruptly. Now here's the complication. On the bottom right, you can see a simulation of that energy release in the tail due to magnetic reconnection. This is an MHD simulation. But you can see this does not extend, depicts the fast flows emanating from reconnection. This activity does not extend throughout the entire magnetotail across. Rather, it is localized in bursts of 2 or 3 RE in extent, in dawn-dusk extent. And so you have to be at the right location to sense the outflows and reconnection. So if you are a few area away, you miss them. So therein lies the need for dense population of this system with multiple satellites. Or if you had satellites lined up at one location and then wait for the activity to happen, and when it happens, you time the propagation of phenomena like flows, information from one location to the other, then you can study it. So, and because substorms are easier to study than their larger counterpart storms, it is the substorms that the community decided to study first in order to learn, and from that process then begin to make sense of the larger storms. So that is how the field decided to proceed back in the early 2000s, and Themis was a mission that was proposed to do just that, that is to look at how energy is transferred from one location to the other and determine what causes the substorm to go off. What process causes reconnection to actually start to happen? And is it a reconnection that triggers the substorm onset, or is it some other plasma process closer to the near region, as it was postulated by many researchers, that is the trigger of a substorm and eventually also causes reconnection to proceed? This was not known because never before were single satellite missions fortuitously at the right location to observe this phenomena from one meridian. But with 5 satellites, one can do that. So here's the 5 satellites that Themis put together at the upper stage of the launch vehicle, encapsulated it, and then launched. All right, so this is the Delta rocket that took the 5 satellites up, and then the 5 satellites used their own propulsion system to go to their final orbits. And the idea was to line the satellites up along the Sun-Earth line and wait there and watch as the substorm is to take off. And here's the substorm going on in a simulation that shows magnetic connection happening, the probes being right there to observe it, and also observing it in the near Earth region, close to the Earth, about 12 RE, and watching which of the 2 phenomena starts first as the auroras brighten on the ground. So there's another element to this whole mission, which is the ground element, right? You've got imagers from the ground looking up, watching the aurora, and ground magnetometers to tell you when the substorm starts, and then timing the space observations to see which process goes off first and is the trigger of the subsequent activity. So that's what Themis did and figured out with timing at 3-second resolution that the first activity is magnetic reconnection, that is followed then by auroral brightening, and then that is then followed by near-Earth activity as the flows from reconnection come to the inner magnetosphere. So we've learned a lot more than just timing from Themis. Of course, timing was a good way to focus the investigation, but you learn a lot more than just that. What we've learned was that reconnection actually causes a, let me see if I cannot stop this. So reconnection causes an activation of the poleward boundary of the aurora. This is like the aurora oval, imaged from the ground up with multiple cameras. And what you see at the bottom light here is the pre-existing auroral arcs prior to the substorm onset. At the high latitudes, this plays again, so it started again now. At the higher latitude, you see the poleward boundary of the aurora. This is the one that brightens first at the time of reconnection onset. That causes a north-south arc. You can see the arc in the north-south direction progressing towards lower latitudes. And when that arc reaches the pre-existing arc, that pre-existing arc breaks up and moves forward, like here, depicting the breakup of the substorm onset, and the poleward expansion of the aurora. So see how the system is all connected. Reconnection and near Earth region are connected by these north-south arcs. They're also called streamers. Meanwhile, in the magnetosphere, what we observe with the satellites is flux tubes that are depicted in gray here in a meridional cut. Flux tubes that are moving earthward, tracked from one satellite to the other, bringing the flows from the reconnection site towards the near Earth region. This bottom one is the equatorial view of that same flux tube, depicting the direction of the flows. So both space and imagers are consistent, and they show the aftermath of reconnection, the fast flows emanating from reconnection, approaching the near Earth region and powering the inner magnetosphere with the energy that comes from the magnetic field, converted into plasma flow and plasma heating. How is this flux tube propelled to move closer to the Earth? Well, reconnection results in flux tubes that are devoid of hot plasma. They come in, the plasma comes in from the lobes where it is very cold, and when it's reconnected, it hasn't been heated enough. And so these are underdense and low, typically cold plasma bundles, flux bundles, that in order to be in pressure balance with their surroundings, they have to be further compressed. They're indeed more compressed. This compression causes the magnetic field inside of them to be increased. The increased magnetic field causes magnetic tension. This tension propels the flux tube earthward. So this is how they're propelled earthward, not by the inertia of the flow that results from reconnection, but by the enhanced magnetic field within the bundle, because the plasma is underdense and fairly cold. This continues all the way to the Earth as the flux tube progresses further and further earthward. And the J cross B forces, pressure gradient forces, were deduced from multi-satellite observations by Themis. These are 3 satellites here on a plane in this simple system that is just a flux tube moving earthward, flux bundle moving earthward. So Shanshan Li here in 2011 was able to deduce these forces and demonstrate they're consistent. That is, the J cross B force, when integrated, results in a velocity that is equal to that velocity measured by the satellite. So we know what propels the bundles. Moreover, as this electric field consistent with the velocity and magnetic field is intense, it takes pre-existing particles and further accelerates them as it moves forward. So particles refract off of the approaching bundle and get heated by the electric field, and the nearby plasma gets heated. That causes what people call injections. These are energizations of the pre-existing plasma to very high energies, and also fresh plasma that comes from the tail. So what you see here is a superposed epoch analysis of such energy versus time spectra of ion injections, electron injections up to tens of kilovolts. As the magnetic field intensifies, the PZ magnetic, the north-south magnetic field becomes more intense as the bundle approaches, as the flow increases ahead of the bundle, as the electric field increases, and as the geomagnetic activity picks up in response. And on the right, you see a depiction of how these bundles coming into the closer to the Earth, crossing the geosynchronous region at 6.6 RE. They accelerate ions, but then grad B drift to the dusk side. Electrons, they grad B drift to the dawn side. And they keep coming earthward and earthward, closer to the Earth. This depicts a simulation of the electric field pulses coming in one after the other. And they bring in magnetic flux at the bottom that gets added to the flux in the inner magnetosphere, distorting the inner magnetosphere region. As the energized ions are very anisotropic, they cause waves. These on the dusk side, they are electromagnetic ion cyclone waves that can be measured by satellites at the bottom left that overpass the aurora. This magenta satellite here is whose data I'm showing in the bottom left. These waves scatter energetic ions. The ions are scattered and then they're propagating along the magnetic field, hitting the aurora, causing proton aurora. That's what the imagers can see in the hazy light at the bottom left. This is proton, or this exactly here is proton aurora. On the dawn side, the electrons that got accelerated are also anisotropic. They cause waves, Whistler mode waves. These waves scatter electrons. The electrons precipitate along field lines to the ionosphere, and they cause pulsating aurora. That's what you see now here on the right, pulsations. This is due to the energized electrons by the dipolarizing flux bundles, or DFBs, as they approach the Earth. So we've learned a lot from multi-spacecraft missions like this. Well, where would they stop? Where would the dipolarizing flux bundles stop? It turns out that one quantity, the flux tube entropy, describes very well the potential of the bundle to exchange its flux tube content with the surroundings and be able to come in earthward, because it quantifies the point where the bundle will stop. It is where the flux tube entropy will be equal to the flux tube entropy in the surroundings. If the entropy is lower, the bundle can still come further in. But if the entropy is equal to the surroundings, it won't be able to be propelled any further. And this was depicted in a study by Dubyagin et al., studying many, many bundles and demonstrating that the bundles stop at the location where this quantity is close to 1, at the location where the flux tube entropy in the environment is equal to the flux tube entropy at the bundle itself. However, they are propelled earthward, they flow past the satellite when that bundle entropy is lower than the surroundings, that is in the distant tail. So in other words, when the magnetosphere is quiet, the flux tube entropy profile as a function of distance has a blue trend as shown here. And when reconnection creates an underdense, underpopulated bubble or bundle with entropy that's lower than its surroundings, that bundle can only move to a distance that's far away from Earth. But when the magnetosphere is stretched, that is when it's compressed by the wind and when energy has been imparted to it, the profile of the flux tube entropy is like what the red curve is here. And so when reconnection causes these bundles, they can move closer to the Earth and be much more geo-effective. So that quantity, flux of entropy, describes well the eventual fate of the reconnection outflows and tells you how geoeffective they can be. What explains the poleward motion of the auroras? I mentioned earlier that the flux bundles bring in new magnetic flux from the connection to the inner magnetosphere. They pile it up in the inner magnetosphere. That changes the topology. That changes the mapping by modifying magnetic models to account for that effect. Sheng-Ing Chu, McFerron, Nikolaev, and others have demonstrated that the auroras, when they move forward, the magnetic field at the equator is distorted such that the satellites at the fixed location suddenly map to higher and higher latitudes following the progression of the aurora. Ignore the moon down here. The aurora that we're talking about is this one on the poleward side. So see, during the progression of a substorm, after substorm onset, when it expands forward, the magnetic field is distorted sufficiently in the nearer region such that the satellites and the activity now maps to higher and higher latitudes, explaining why the auroras also map at higher latitudes. So at the bottom picture here, you see a latitude versus time progression of the auroral light at one meridian. You see the aurora moves forward, but simultaneously with that forward progression, so do the satellites, which are at fixed location at the equator, move forward because of the distortion of the mapping due to the incoming flux. So you see now how multi-spacecraft missions like this that are enabling judicious tuning of magnetic models are able to explain global structure and the progression of a substorm. Multi-spacecraft missions that are equipped with propulsion also have the advantage that they can be reconfigured. So of the 5 Themis satellites, 2 were quickly becoming obsolete because differential drift would now change their orbits sufficiently. We couldn't use them with the other 3. So we decided to use their propellant to take them further up rather than bringing them down, further up and go to the moon with them. So we used them to go around the moon, use the moon as an anchor point, and then use them from thereafter to study the midtail region at 60 Earth radii. And they've really changed their views of how the magnetotail works. For example, they demonstrated from that location that you can integrate, you can detect, record the total magnetic energy in the magnetosphere at any given time during a substorm, and compare that with the energy release that's happening at these diverging flux bundles, at these reconnection quote-unquote fronts, and showed that the energization that is happening on the tailward side, the tailward outflows, is 10 times smaller than the energizations happening on the earthward side of the outflows. The reason being the magnetic field is much stronger on the earthward side. And they put that in context of the global energy during a substorm, demonstrating that, yes, these energizations at the reconnection fronts can account, when integrated, can account for the total energy conversion during a substorm. So that's what's causing energization in the near region. And I'm calling them fronts because they resemble weather fronts in atmospheric weather. This is where the energy is. This is where the action is. But really, I mean the fast flows emanating from reconnection or dipolarizing flux bundles coming towards the Earth. Same thing. Okay, meanwhile, in 2015, one of the key mysteries of what's causing reconnection to eventually happen was resolved by another multi-spacecraft mission, MMS. And you need multi-spacecraft in this case because you need to determine what the current is from 4 satellites, 3 dimensions, determine the curl of B to find J. And from J dot E, you can determine where energy conversion occurs. MMS did that handsomely at spatial scales that are comparable with electron scales, that is electron gyre radius, electron inertial length, and determined that the origin of the breaking of the field line, that is the resistivity related to the non-ideal terms in Ohm's law associated with reconnection that's causing the field line to become untied from the plasma is due to the non-diagonal terms of the pressure tensor. And so out of many possibilities, it determined what is the one physical process that's causing reconnection to occur, which is really a very important progress in the field, because what we learn here at Earth can be applied to other astrophysical systems, such as at the base of the solar corona or at other astrophysical settings. And it did so by measuring distribution functions of the electrons that show the precise age aerotropy and gradients in the phase space density that are predicted for this particular model, non-diagonal pressure terms of the non-diagonal terms of the pressure tensor, to be the correct one. So the measured distribution functions of electrons, both at the day side magnetopoles where reconnection occurs, and at the night side magnetotail where reconnection occurs, both have the imprints of this process in them. Major progress. Since 2015, the community has been able to utilize the existing assets to form a large-scale heliophysics system observatory. And that observatory was able to coordinate measurements from Themis, MMS, and international missions to put together a comprehensive view how the system works as a whole. Moreover, it has been able to apply such data towards understanding storms. This is a case of a storm that happened about 12 months ago, when Themis was at the right pre-midnight location. The Korean COMPSAT satellite and the Japanese ERG satellite were here at the same meridian, and they detected very near Earth reconnection, that is 8 to 9 RE, powering the main phase of storms. The storm main phase is detected here in the disturbance storm time index, DST, and it is accompanied by large-scale auroral electrojet index intensifications shown here, and it is detected by very abrupt, impulsive changes in the magnetic field that you see here, here, and here, and fast tailward and earthward plasma flows. That's the detection of very near reconnection, never been seen before so close to the Earth, that happens during storms. So like the classical near-Earth reconnection that occurs during substorms, that happens further back at 25 RE, during the main phase of storms, very near-Earth reconnection is most common at pre-midnight. So we learn a lot from substorms that now can help us to study storms. But moving in the future, we really need tetrahedral formation, satellites that are able to measure gradients in the pressure, currents, and vorticity to be able to tell how this energy that is emanating from the flows is converted then to plasma heating and powers field line currents that drive the ionosphere. For that, future missions such as the Plasma Observatory, current contender for the ESA M7 program, MACON, which is under study by the Decadal Survey, and THEA, which is a future MIDEX proposal, are all destined, planning, wanting to do just that. So, and you can see where we're getting at. We're motivating by fields like oceanography that has deployed thousands of buoys at Earth's oceans and completely transformed studies of ocean currents, salinity, and global circulation models, atmospheric models, by providing the right inputs to understand this vast system, vast interconnected system of oceans and the atmosphere. And we need to do something like that in space with hundreds, if not thousands, of space buoys. Can we do that? Well, perhaps the first step would be an ionospheric constellation that has reconfigurable satellites on the order of a few dozen that can study spatial scales of gradually from one to the other and go after specific scientific objective at each phase with proper imagers in the north and south. To do that, we need to take advantage of CubeSats because they are up and coming. This CubeSat revolution is demonstrating, bearing fruits, because you've got now an exponential growth in satellite launches, in launch opportunities. At SpaceX alone, we've exceeded 100 launches this year, and with multiple orbits being able to be attained from a single release using this Sherpa ring, that is a propulsive interface that can take satellites to their final position. We have many opportunities of populating the magnetosphere with CubeSats at various locations. These technologies are disruptive because just like the PC disrupted mainframes, digital cameras have disrupted chemical film. They too can disrupt the main satellite business because once they attain sufficient market foothold, they expand their customer base, they have a wide range of capabilities, then they disrupt this technology. So this is where we're getting at with CubeSats like CSSWE from Colorado, or the Firebird satellite from Montana State, would have done high quality science with low cost missions. Now it is possible to think about constellations of those. Elfin was such a mission that has also demonstrated the importance of monitoring the magnetosphere from low altitude orbit. The complexity in the magnetosphere can actually be monitored from the ionosphere, as I will show you momentarily. Elfin was a two CubeSat mission that allow us to do that, to demonstrate that. It was launched with a very, very focused objective to understand if relativistic electrons from the outer radiation belt can be scattered by electromagnetic ion cyclone waves. But there are many, many other waves and processes that can cause scattering that could also be measured by Elfin, such as chorus waves, His waves, ULS waves. All this could be studied by Elfin, and they were studied in a series of more than 40 papers. And so the reason why it's so powerful is because you can measure the loss cone with far more easily from low altitude, where the loss cone is about 60 degrees, rather than at the equator, where the loss cone is 1 degree. Understanding the pitch angle and energy spectrum and understanding what wave process caused that spectrum is a very powerful way of telling what happens in the magnetosphere from the ionosphere. And so by using its single detector, but by spinning to form the pitch angle distribution at every spin, Elfin's ion and electron detectors were able to do just that. So here is an orbit of Elfin, Here is an image of Elfin, and here is a product of Elfin. It's energy versus time spectrum of the flux at the top, and the ratio of the precipitating to trapped particles at the bottom. You can see it's red when it's 1. This means a lot of scattering. That tells you where the plasma sheet is. It also tells you where imic precipitation is, because the scattered electrons are the highest energy. So that's imic precipitation. But if the scattered electrons are low energy, as you see here on the right, that's Whistler-driven precipitation. So by doing stuff like that, you can determine what the fingerprint of each process is at any given magnetic local time sector and latitude and activity level. So you can distinguish chorus waves, quasi-periodic chorus, wisp emissions, His waves, the isotropy boundary, and various plasma regions in the magnetosphere. So a really very powerful way of determining what's going on in the magnetosphere. You can also tell how a substorm evolves from the ground up. So here's the substorm seen in the super mag L index. It's like the AE index. It's telling you where the substorm growth phase is here, the black line trending down. The expansion phase is this abrupt change in the black line down. And the recovery phase is this gradual retreat back up of the black line. During these times, the red marks, Elfin passed by the pre-midnight sector and detected radiation, outer radiation belt, and plasma sheet, and determined that the tail dipole transition region, depicted by this arrow here, it shrinks during the course of the growth phase and expands during the course of the expansion phase, just as the models predicted. So it's a very powerful way of determining what the evolution of magnetospheric configuration is during a substorm. So not only can you tell waves, but you can also tell processes from the ground, from low Earth orbit up. In the meantime, you can train your workforce of the future, empowering students and testing new technologies. So NASA has been embracing such technologies for future constellation missions. For example, it launched the Cygnus satellite system in 2016 to do atmospheric science. It has approved for launch Helioswarm in 2026 in the solar winds, 8 microsatellites and a hub. You probably know it's a MIDEX, and it is approved for studies, phase A studies, for a SMEX mission, this Cinema mission, 9 CubeSats. So a great field, a great time moving forward to study with multi-point observations this complex phenomena. So what have we learned and where we are going? We've made tremendous progress in the last 15 years, understanding how the inner magnetosphere is powered with multi-point missions. We have learned that substances occur a series of reconnection impulses that are initiated at 25 RE, sending flows to the tail dipole transition region where the pre-onset auroras lie, and there they initiate the onset. The forward expansion is really a leap forward due to magnetic mapping distortions by the magnetic flux that's coming to the inner magnetosphere. We've learned that reconnection initiates energy conversion that can power the inner magnetosphere thanks to the low entropy nature of the reconnection outflows. And we've also learned that such reconnection, but very close to the Earth, is implicated during the storm main phase. What we still need to understand is what are the kinetic aspects of that energy conversion, because that requires truly tetrahedral formation missions that in 3 dimensions can sense the pressure gradients, currents, and vorticity. This is still to be done in the future, but low altitudes can help, both in terms of monitoring the near-Earth environment and in terms of building the technologies that will enable constellations of the future. And therein lie university CubeSats that can help in that regard by becoming the training ground for future space explorers, while also allowing us to validate new technologies. So thanks for your attention and look forward to your questions.
Thank you, Vassilis, for this, wow, excellent talk. I think it's really challenging to cover this topic in 45 minutes, and you've succeeded. Congratulations for that. Let's now go through the questions. I've got several questions. I'll go through the lists, and I will ask you to unmute your microphone when I call your name so that you can speak up. I think it's nicer than me trying to read out your questions. So we start with Umberto Rolero. Umberto, normally you should be able to speak.
Yeah, can you hear me?
Yes.
Yes.
Go ahead.
Yes, I just had a question on the duration of the magnetic reconnection event. Is it because you mentioned that substorms are impulsive, but I was wondering, is this then magnetic reconnection impulsive, or what is its typical time duration?
Yes, it is impulsive. It is the origin of this impulsive nature of substorm onset, and it's also the bane of our existence. It's why it's so difficult to observe, because it turns on and off, and if you're there, you observe it, but a minute later you cannot. So you have to be at the right place at the right time. So it lasts on the order of seconds to minutes. It turns on and off, and it occurs in intervals of maybe a few minutes at a time, 5-10 minutes, and then it moves on to another location. It starts at some region, as I said, 25 Vari, but eventually it gradually moves down the tail, because the flux that it imparts to the inner magnetosphere builds up, it piles up, and so it prevents reconnection further, down the tail. So reconnection can only then occur at further distances. So you can see it is sort of a wave of reconnection that is impulsive and moves tailward as the substorm progresses. Okay, some
Thank you.
other details, is substorm expansion phase lasts about half an hour. In that half an hour, reconnection will occur intermittently at various locations in the magnetotail. Never at the same, very rarely at the same location. It will last at one location. It may last, as I said, a minute or two, and then it'll move on.
Okay, so let's move on with Ivan Dimitri about high energy particles. Ivan?
Okay, can you hear me?
Yes,
Yeah.
go ahead.
Okay, fine. So my question is concern particles. So it's maybe a bit not really on the topic. So I'm wondering if I should expect some variations in the fluxes of electrons and protons in low Earth orbit. I'm thinking to electrons and protons with hundreds MeV energy. And if I have some tool to measure those fluxes in a low Earth polar orbit, my question is which kind of effect, if any, I should expect during those extreme events.
Okay, yeah, thank you for that.
If these observations are useful or not.
Yeah, so let's see, the cross-tail potential that is responsible for energization in the near region is on the order of 40 kilovolts, 50, 100 kilovolts, no more. Thanks to wave particle interactions, we can get up to energies of MeV, multi-MeV for small population. Beyond that, energies above, say, 10 MeV or so, typically are coming from outside the magnetosphere, from the solar wind or from astrophysical objects. So galactic cosmic rays and such. We still observe them in the, at low altitude. We observe them, but we do call them solar energetic particles or galactic cosmic rays. They are not attributed to magnetospheric processes. So hundreds of MeV to GeV are external. They are observed because the gyradio of these particles are so large that they just are blind to the presence of a magnetic field. They just come right through and they hit the Earth.
Yes, of course. My question is if the fluxes of those particles should be influenced at very low energies, so even few MeV by this kind of storms that you described.
In the sense that the storm is induced by a solar wind change, magnetic field, the coronal mass ejection is very large scale and can affect those, cosmic rays coming in. Yes, but in the sense that the local magnetic field would affect them, no, because too small a scale to affect such large radii. But the heliosphere can affect.
Yeah. Okay, thank you.
Sure.
Okay, so we have another one by Jason Durr about ionospheric signatures. So Jason, you can unmute. Yes, go ahead.
Hello. Yeah, so I'm wondering, I guess, two sort of related things. First of all, are there any ionospheric signatures that allow us to distinguish between steadier or more patchy reconnection? And then, again, related, does the steadiness of the reconnection have any implications for like how bursty the bulk flows are, like how many bubbles there are, as opposed to like, say, some steady large region of flow?
So the ionosphere, to be able to tell from the ionosphere if a reconnection is unsteady, you need to be able to observe one spot for a long time. This means not a single satellite, unless you have a succession of satellites, right? You have satellites on a string of pearls in a single orbit, 10 of them, and one after the other, arranged so that a minute or two later, another one passes, and a minute or two later, another one passes. So you can deduce what is the temporal variation as opposed to the spatial variation due to the motion of the satellite. That can be done with constellations, but ideally you want an imager. Imagers can be auroral imagers, okay? They can tell precipitation. They can potentially deduce reconnection if we ever understand what the auroral signature of reconnection is. But there are rheometers that can also do stuff like that. So imagers would be a better way to observe from the ground up a region of the aurora and deduce whether reconnection is impulsive or not. Both of these can happen. They're out in the future. They have not really been done before. No? So to tell whether what is the repetition rate or the time scale of reconnection from the ground up. For that, you need equatorial spacecraft. Now, can we deduce what is the extent, duration of reconnection from local measurements in space? Only constellations can do that, and only hand in hand with simulations, I think. There is one potential way of deducing spatial extent, and that is remote sensing with energetic particles that have large gyroradius to remotely sense hundreds or thousands of kilometers away, depending on their energy. That potentially is possible with some modeling. Generally, these things are very difficult to do, though.
All right, could I just to clarify my second question, I guess one thing I'm wondering is when you've got unsteady reconnection, is it possible or, maybe even known that that's what's causing individual bubbles and flow bursts in the BBFs as opposed to, say, a steady stream of plasma that like you might expect from just continuous reconnection?
Yeah. My impression is that reconnection itself is unsteady, and it is not like a continuous process that's moving about that gives you the local variation in the measurements. It's very hard to prove that. but that's what I believe is going on. Very hard to prove it.
All right. Okay. Thank you. Very, very interesting.
Yeah.
Okay, we have a easier question by Nuno Pereira about the distance.
Hello?
Yes, go ahead, please.
Yes, the first part of the question you already answered. It's about to what distance from Earth do substorms usually happen? Well, you say that impulses start at 25 Earth radii and then flows at 10 around. But the point will be if they, in practical terms, they can seriously impact the geostationary satellites at around 6 Earth radius, and also if the solar maximum can enhance these solar storms, these substorms. Sorry.
Well, the answer is yes to both questions. Let me start with the first one. Can these flows come to the geosynchronous region? Absolutely. During the main phase of storms, I think this is what's happening. In fact, we have some published work that shows the penetration of such flows to the inner magnetosphere inside of geosynchronous. They're the most geo-effective. They just directly power the ring current. And they happen partly because reconnection at those cases during main phase of storms is so dynamic that it actually starts very close to the Earth. It starts at 8 RE, not at 25 RE, but at 8 RE. And from there, it has direct access to the 6.6 RE geosynchronous or inside of it. See, this happens because the magnetosphere is so compressed by the wind flowing by so fast and having such a high density that the tail, magnetotail itself, is inside of geosynchronous. Geosynchronous magnetic field is tail-like. It's unusual. Like geosynchronous satellites can actually exit the magnetosphere on the day side. So compressed is the magnetosphere that the magnetopause is at 5 RE. So you can imagine on the night side, the dipole does not extend beyond 5, 6 RE. That's why I'm saying, yeah, of course, the tail flows can actually make it inside of geosynchronous. You asked me the second question. Could you remind me again what that was?
If the solar maximum
Yes.
can enhance the strengths of these substorms.
Yes. Well, substorms are enhanced and much more dynamic, and storms are, of course, occur during the peak of the solar activity and the declining phase. The most damaging effects come from coronal mass ejection. They pack a pretty big punch because they contain very strong magnetic fields, so they're electromagnetically very energetic. But also stream-stream interactions also occur, and they peak during the declining phase of the solar cycle. And both of these cause major storms, but also substorms. And the substorms are in fact, series of substorms, one after the other, due to large-scale authentic waves in the solar wind, can cause as much havoc to satellites as main storms do, because they collectively and cumulatively carry so much energy that they heat electrons over timescales of days to energies, multi-MeV energies. And so they really enhance the outer radiation belt, even in cases where the ring current has not been completely very much energized. So you may not have magnetic storm, but you can have a very intense radiation belt.
Thanks.
Sorry for that. So let's move on to Mika Holmberg. Mika?
Yes, so
Yes.
my question is about the motion of these particles once they reach Earth's atmosphere. So the acceleration starts out in the magnetotail, but then when they get closer to Earth, they should get closer to their mirror point, I guess. So is the velocity component then mainly perpendicular to the magnetic field, or is it parallel to the magnetic field in the region where the aurora is created?
Now, these particles, you can think of them as energized. As the flux tube comes in, they kind of, to zero order, they stay within that flux tube, bouncing back and forth. And to zero order, they get scattered and isotropized at the same time, either by field line curvature or by waves. So as the flux tube propagates inward, at the same time, particles leak out of it and power and hit the atmosphere. But because the loss cone is so small, that they cannot be depleted. So they maintain a decent amount of flux as they move closer to the Earth. So they they power the ionosphere, all the time as they come in, and their energies, MeV and above, can reach altitudes down to 60 kilometers or below, and in fact get down to the stratosphere. So they do have important effects like atmospheric ozone depletion and global cooling, and they really need to be included in global circulation models. They should be. So for future fleets of satellites like that can help not just magnetospheric physics, but also atmospheric science.
Yeah. So
They are not being included now, by the way. We're missing out on that component, but absolutely is necessary for future GGCMs.
So suggest we move on with a question, or actually several questions. It's an evolutionary question, actually, by you, Hudson. You, if you can unmute. Yes.
Right, if I'm unmuted, can you hear me?
Yes, fine.
Okay, so I've always been a fan of these analogies between solar flare. I'm a solar person, and so the analogy between the substorm and the solar flare has always been, for more than half a century, it's been of interest, but it's never really gone anywhere. And so I'm wondering, since you mentioned it, if there's any literature, any results that you can quote where this has been useful. And just to continue and take up my second comment on the chat window, I was amused by the question that was asked about 300 MeV particles. We get those in solar flares all the time, not just in SEPs, but also in the closed field regions that have nothing to do with galactic cosmic rays. And so there is an intrinsic capability in the processes involved in flaring that produce these high energy particles, which you apparently don't see in the magnetosphere.
Yeah, no, thanks for that question, Hugh, and good to hear your voice. There is a paper by Marco Velli. He had beginnings of an institute to study this connection between solar flares and magnetospheric substorms. The scale sizes are the same. Amazing. Like the solar flare at the initial stage is the same size as the magnetosphere, but the order of magnitude difference in magnetic field is 5 orders of magnitude greater magnetic field intensity, and so 10 orders of magnitude greater energy density. And so you can see why the energization is so much greater at the flare. There's just so much more energy associated with that.
Oh, but there's zero cross field electric, cross-tail electric field. In flares, there's nothing like that. There's no solar wind in solar flares, if you can pardon my comment. So we don't have the driver. We don't have the electrostatic driver for high energy.
Yeah, but aren't the lateral motions in the solar photosphere that impart a similar kind of compression and energy input?
Never described, no.
Oh, well, maybe that's what people should look for.
Well, I think that it's not fair. This is just people most of the theory on the solar side is MHD theory with no electrostatic potential. And so you're not going to get any plasma physics out of this kind of approach, I don't think. So in that sense, the analogy may be there, but it would be very nice if people would, the solar people, I guess it's our fault and not to pick up on the kinds of good ideas that you guys have.
It's hard, you cannot visit those regions, so you can only rely on imaging and what you can deduce. But yeah, check out that paper by Marco Velli, Anton Artemiev, and others.
You're not asking me to believe anything Marco says, are you?
Okay, we are soon running out of time, but let's take maybe one or two more questions. One by Marcos Silveira. Marcos.
Hello, can you hear me?
Yes.
Okay, great. Thank you, Vassilis. My question is about is there any special conditions for this very near reconnection line happens that is different from they used to know as a near Earth reconnection line?
Special conditions must be sought to be found. And the clue is that they happen only during the main phase of storms. Never have they been seen in the recovery phase of storms. It is very strange. It must be
so
that
they are not the,
yep.
They are not the trigger for they are not the trigger for the magnetic storm. That's what you mean.
I'm sorry, could you repeat the question?
They are not the trigger for the geomagnetic storms. They happen during the magnetic storms.
They happen during the magnetic storms. There is no such thing as a trigger, I think, for the magnetic storm, because it is basically the impacting the CME impacting the Earth, or the shock impacting the Earth. As soon as the IMF turns southward, in that process, energy gets in, and it's so dynamic that tail reconnection starts immediately thereafter. There is no loading phase, but it waxes and wanes. And so during the main phase, it could be continual reconnection in the sense that it happens at one spot and it happens at another spot. And so these impulses of reconnection, very near reconnection, VNERCs, occur at various locations impulsively. And the aggregate is what we see as the main phase of a storm. So I don't see, so yeah, I mean, they're all sort of self-regulating, self-organized. And so, but it's also very difficult to discern because they're so intense that very hard to study one and isolate it from their surroundings.
Okay, thank you.
Yep.
Okay, I suggest that we take one last questions by Evgenios Stefanidis. You can, okay, if you unmute yourself, you can talk. Yes, let's go.
Hello. Hear me?
Yes.
Nice. I would like to learn more about the ELFIN mission and its findings on precipitating electrons. So do we now have a clearer understanding of the energy levels of precipitating electrons and the altitudes and latitudes at which they are observed? And what is the significance of understanding these parameters?
Yeah, no, thank you for that question. A lot has been, a lot of progress has been made in characterizing the energetic electrons using ELFIN, because 4 years of data, 12,000 passes under a variety of conditions, storms and substorms, with both ions and electrons. So wonderful data set. The statistics have not been completed in terms of creating models, but we're close on that. Yeah, I think if you look at the ELFIN website, you'll find many, many papers that describe the energization of electrons, precipitation of electrons due to various processes, all the ones that I described, have been already very much advanced. So yeah, we know what the fluxes are typically now for various processes, and we know how we can incorporate them in future models for the use by as inputs to circulation models.
Okay.
Okay, thank you.
Of course, yeah, it'd be nice to get more of them and get them in an operational sense as monitors of space activity to help ionospheric and atmospheric science.
Thank you very much.
So thank you to all the speakers for the people attending for asking all so many questions. I'm sorry, there's still a few questions left in the chat, but in the interest of time, we should stop now. You can contact Vassilis if you would like to ask these questions directly. The talk will be available very soon, in a matter of days, on YouTube. And let me just tell you that the next and last webinar of the year will be on December 5th on the use of AI in Earth observation. With that, many thanks again to you, Vassilis, for managing to handle this complex topic.
Thank you. Thank you for the very interesting forum and very nice questions.
So thank you very much to everyone and to you in particular.
Thank you.